of actually taking the papers out of his hand. Okay. So don't chat too much about the quiz because there's some folks out there who have to take it later. So don't give away any of the fun secrets. All right. So what we're going to do today? Well, okay. So we've got a few things we've got to talk about, kind of wrapping up some topics from QED. As you might have noticed if you did the pre-lecture reading, which I posted about 20 minutes before class. But I did, in fact, get it up there. So we've got a few topics we're going to wrap up with QED, and then on Thursday, I haven't quite decided yet whether I want to go straight to renormalization or whether we want to talk about QCD. But we have 3 lectures left in the proper class time. But you know what I figured out just the other day, this illuminating thing? It's awesome. We have a 2-hour exam period where you're all guaranteed to be available, except for maybe Patrick, who might be out of town. But so I could actually have a last lecture during the exam period. Jacob's like, no, why? Why are you shaking your head so much?
I got things I got to do
during exam period. Oh, actually, I don't even know when our exam will be. So I'll have to look at when it's going to be. Because if it's at 8 a.m. Saturday morning, I ain't going to hold no. But anyway, that would be an option to be able to get in the material that we sort of missed in the middle of that snow day and all that other crap that happened. So, but we'll see. All right, but I have to get through these few things today, no matter what.
When are we going to be getting the take-home exam?
I'm going to give that to you. Let's see. I'm probably going to aim to give that to you Tuesday of next week, and then it'll be due. I'll give you at least a week to work on it, but it depends on when I have to look at when our exam. Does anybody know when our final exam is in this class?
Have the final exam schedule on them?
It's probably maybe
on Wednesday.
It's on a Wednesday. Okay. Yeah. So anyway, I'm not planning on beating you guys up for the rest of the semester. So all right. First of all, before I get started, we're kind of picking up halfway through a calculation. So if there are any questions about how we got to where we got to last time, of course, if you did the homework, you repeated several of the crucial steps that we just talked about last time in getting to where we're going to start Monday. So
Monday, 10 o'clock.
It's Monday at 10 o'clock.
It's 8 a.m.
I think it's 8 a.m.
You're very wrong, Jim.
What?
I don't know if you know.
You're lying. He is lying to make it.
I am looking at this one.
You're just bad at it.
Oh, I'm looking at the wrong bar. Yeah, no bad.
So it's Wednesday at 8 a.m.? Oh. We'll have to see about that. Science. Okay, so we're going to continue with the example of electron-muon scattering. And just to have a concrete context in which to couch our discussion. So right now we're considering the lowest order contribution. That's stupid momentum labeling spin files. No idea why I did that. Okay. So we were in the process of evaluating the lowest order contribution to electron-muon scattering, and you know, one of the reasons I picked this particular process is because this is the only second order diagram that contributes. You can't turn it sideways, and neither can you twist any of the outgoing or incoming legs. So it's the only one, and then that simplifies the analysis when we square M, because we don't pick up a whole bunch of cross terms because there's only one contribution. Of course, there are higher order diagrams. So if you're really calculating M and you want to do it accurately, you would have this contribution, which I might call M1, or actually we tend to call it M tree because it's the tree level contribution, plus contributions with loops. but this is going to be the most dominant contribution, so we're just going to focus on this one for now. So we had followed the Feynman rules, constructing the spinor sandwiches, following the matter lines, putting in vertex factors when we encountered them, throwing in a propagator for the internal photon momentum. And then we spent a lot of time last time taking our expression of spinor sandwiches and then saying, okay, we would like to average over the incoming spins and sum over the outgoing spins. And so to do that, we utilize these completeness relationships for the spinors that, again, you worked with in your homework. And then we found this nice result that if you want to average over the spins and construct this quantity, where the brackets here mean average, not expectation value. Okay, so we have to square m. We have to take the complex magnitude squared of m, and then we're averaging over the incoming spins, summing over the outgoing spins. To do this, we can just replace these spinor sandwiches where we see them with trace expressions. So I'm going to go ahead and write down where we ended from last time. So this expression will be straight out of your notes. And I am going to adopt the slash notation just to avoid having to write a lot of indices. And hopefully from your homework, you glean why that's useful. Otherwise, when you write out these expressions, you have to put just a ton of indices everywhere. But if you use the slash notation, if you use the slash notation, you don't have to write this as with an index. So remember, anytime you see slash, that actually secretly corresponds to gamma with some index. I'll call it beta p to eta. But since these are summed over, they're always going to be the same. They have to be different than all the other ones. But we're running out of choices. I've got so many letters in the alphabet, so we can just forgo writing those repeated ones and just call it slash. So the slash notation is very handy, especially when you get these larger expressions with lots and lots of potential indices. Okay, so are there any questions about this expression? It's kind of the last thing that we wrote before we left last time. All right, so we're going to do two things today. One is we're going to evaluate this. We're going to actually take these traces, okay? And then once we've evaluated this, the final form of it will involve nothing but good old form momentum. There'll be no spinor stuff left, period, end of story. But once you have an expression in terms of just form momenta, that is primed to be stuck into the golden rule, because the golden rule is asking you for an expression in terms of form momentum, some of which it integrates over, others of which it sums over, etc., or a sign. So we'll evaluate this down to expression in terms of form momenta, and then as a second step, we'll plug it into the golden rule, and we'll actually get a really concrete result. So to evaluate this, we're going to need some trace expressions. I gave you a handout with a lot of these trace expressions on it. This is just out of the book. Whose name did you not speak? And we're only going to use a few of them today. Some of these you've actually proved in previous homework, but the ones that are going to be particularly handy for today are the trace of product of 4 gamma matrices. Actually, I'm not even going to write it. You can I'll just write down the trace, and then you can see what it is on the sheet. Okay, you see the expression for that on your sheet? Should be a bunch of factors of the metric. And again, he writes the metric as G. And we should appreciate that that's actually secretly eta because we're using the Minkowski metric. So everybody see the formula I'm talking about? We are also going to make use of the trace of 3 gamma matrices. Can anybody tell me what that expression looks like? See again? Say it loud. It's 0. Okay, one of the trace theorems on that sheet is that the trace of a product of an odd number of gamma matrices vanishes. And then lastly, we're going to make use of the trace of 2 gamma matrices. Which if you look on your sheet, you'll see is 4 times the, it's actually 4 times the inverse metric. But, okay, so we're going to use these 3 results, and you can see them on your equation sheet. So let's see how we're going to make use of them. Now this expression on the board looks intimidating, okay? But don't be intimidated by it. Let's just go through for a moment. Cut it out already? Can people stop being sick? It's getting on my nerves. Do you realize what it's like to be a teacher in a class where a lot of people are sick? It's like all of your stuff is aimed at me. It's like I'm the target of your sneezes and your coughs and your projectile line. Okay, so I know this expression looks complicated, but let me just go through the pieces for a minute to kind of comfort you before we actually dive into it. This is a number. This is certainly a number. This is just a coupling constant to the 4th, and this is the difference of 2 4 momenta to the 4th. Okay. Now, this quantity we're taking a trace in spin space. So that means that in spin space, this thing is probably some kind of matrix, and we're tracing it. That this is a matrix we can see because every gamma is a matrix. And in fact, these p slashes have a gamma in front of them. And in fact, when you see an MC, we have to go ahead and stick in an identity matrix there just to make the sum of these 2 things consistent. So secretly, this is just overall a sum of 4x4 matrices in spin space. If you multiply all this out, you just get a sum. So you're adding all those matrices together, and then you're taking the trace. And then you're doing the same thing here. You're multiplying those 2 results together, and then these 2 factors of the metric just come along to take up all of these unsummed indices of the gamma factors. Now, the space-time indices and these metric factors, we're free to move around because we're evaluating them using the Einstein summation convention. And that's the beauty of the summation convention, is you don't have to worry about order. However, the matrices in spin space, we're actually going to implement them as true matrices, and so the order in which we write things matters. We can't just move things around freely. So we have to, when we wrote this expression down, we were very careful to follow a procedure to get things in the right order. Okay, and when we, for example, Hermitian conjugated, we had to reverse the order of things in various places. So I want to make sure I can maintain the order of matrices, but anything that is a number in spin space, I'm free to whip outside of expressions, keep in expressions, reorder however I like. Okay? So with that in mind, let's start by taking a generic version of one of these traces. So if I just take a trace of something I'll call this, and we can apply this to either of the 2 traces because they have basically the same form. I'm going to call this x, all right? And the first thing I'm going to do is I'm going to see if I can reduce x to an expression that doesn't have any space with it. And then once we figured it out, we can apply it to this trace, apply it to this trace, and then finish off writing the expression, okay? So some useful trace properties. If I have 2 matrices or more added together and I'm taking the trace of their sum, how is that expressed in terms of the individual traces of the matrices themselves? It's the sum of the traces. So I can always break this up into the trace of A plus the trace of B. So that means I can multiply this bad boy out, take it as a sum of a bunch of terms, and then just take the trace of each and every one of them. Okay? So with that in mind, if we do this with x, then what we're evaluating is now one very, very non-trivial result. which I'm going to go ahead and tell you, and then you can prove to yourself, is, so does anybody remember the definition of gamma bar? Let me see, Nicholas. Last time, actually maybe even the time before that, I gave you a definition of what I mean when I write bar over a matrix. Can you remind me what that means? You being in it's probably, you probably see it somewhere like that. This is just a particular example where the gamma is just literally a gamma matrix and nothing else. Does anybody remember?
Gamma naught.
It's like gamma 0, then equal gamma, or whatever matrix is emission conjugate.
Yeah, so remember, to form a dual spinor from a spinor, we Hermitian conjugate it, multiply it on the right by gamma 0. Well, this is a matrix in spin space, and so the fact that you have to sort of apply two factors of gamma 0 is sort of the thing that we see when we transform matrices versus vectors with rotations, for example. So this is just the definition of what that bar means. Now, normally, the thing I'm about to write down is not true in general for something like gamma, where this is not necessarily a single gamma matrix. Okay, but if this is just a gamma matrix, then this turns out to just be the gamma matrix itself. Okay, that is not generally true that the bar of something is itself, but if it's just a direct gamma matrix, that is a nice property. Okay, so the bar is going to disappear in the subsequent expressions. All right. That's why I point that out. Okay, so going back, I'm multiplying this thing out, and I'm just taking it a term at a time, and I'm tracing each one of them separately. So I end up with a sum of terms . So you might not have had time to multiply that out, but if you did, that's what you would find. Anybody have any disagreement with any of those terms? Anybody at least comfortable with where they might be coming from? Okay, now is where it's important to remember what things are and what you can and can't move around. So there's another property of traces that is very nice. That is, if I have a scalar times a matrix and I'm taking the trace, the scalar just comes out as an overall factor. Okay, that's a scalar in the space in which the M is a matrix. Now, why do I say that? Well, these things right here are just scalars in spin space. So I could always take these factors of M, wherever MC, wherever they occur, and actually pull them out as coefficients of the traces using this property. But it gets even better. Yeah, Alex.
But you're leaving the hidden identity inside.
Right, but that hidden identity is not going to affect anything.
Right.
You're right, yeah. Okay? You're going to see why I do that in just a second. But it gets even better than that, because all of these P's what? Yeah, I'm getting there. I was really hanging on the P, like I really want to write P. These P's are scalars in spin space. The only reason P slash is a matrix is because of that gamma sitting in front. So if I take all of the P's that I see and I break them up now, the momentum part I can pull out as a coefficient of the trace. So if I pull out all of the momenta, just the momenta, I leave the gamma matrix in. If I pull out the momenta and the mass factors, I'm going to be left with traces over what? Products of gammas. And that's where these expressions are going to come in handy. Okay? Now, I just take a moment and understand why we can do this. This is why throughout this course I've really pushed on know what is trivial in a certain space and what's not. In spin space, you have things that are matrices. Those are gammas, and then you have spinors, the U's and the V's. Those things are non-trivial in spin space, but everything else is effectively a number in spin space. And so for the operation of trace, I can just pull it out as a coefficient. Okay, now with that in mind, here's what X becomes. And there's going to be a lot of index assignment because as I break up these P slashes, I have to actually give them indices. And I have to be very careful that if I take out a P here and I leave behind a gamma, that the P that comes out and the gamma that I leave in have the same indices because they have to be summed. Okay, so the assignment of indices is very precise in what I'm about to write. So here we go. Okay, so it's going to have A, alpha. Alpha is the index that gets summed with a gamma index. And then similarly for beta. See a furrowed brow.
Is that minus sign?
I think I actually just lost it on my the pen in my notes. Mu, lambda, yeah.
I bumped it with the eraser of my pen and my
Notes. You're going to figure out in a second that it doesn't matter. Okay? Is everybody on board with that? I just broke up the P slashes, pulled out all the P's, all the M's. Joe?
What's the index thing on the third term?
Third term.
Is that PB alpha? Should that be a PB beta? Doesn't that come from the same PB beta P slash?
Wait, you're talking about this term?
Yeah, that term. Doesn't that come from that same P slash as the PB beta in the first term?
Yeah.
Yeah, it should be
I see what you're asking. It doesn't matter. In fact, I'm being a little bit sloppy because technically, when I write an expression, I should never be repeating some indices in. I should never be repeating an index in an upper or lower location. It should always be one up and one down. So I'm being a little bit cavalier because I know where I'm going with this, but I really should have given this a label beta and then given this a different label altogether. Okay. And I mean, for those of you who aren't clear why that's a bad idea, if I write this, P1 mu, P2 mu, gamma mu, right? This is not the same as P1 mu, gamma mu plus P2 alpha, or gamma alpha. What's the difference?
That one, the first one gets summed over entirely.
Oh, actually, you know what? I'm sorry. No, it's actually. I'm sorry. It's actually fine when you're adding things. Sorry, it's when you multiply things that you get screwed up. Adding things is actually fine. Okay. And since I'm adding these, it doesn't matter. When you multiply them, so if I were multiplying these two quantities, these would be very different. Okay. That's something that you probably saw in the homework. Okay, because this would not have cross terms. You would do 1, 1, 1, 1, and then 2, 2, 2, 2, plus 3, 3, 3, 3. Here you do 1, 1, 2, 2, 3, 3, 4, 4. Separately 1, 1, 2, 2, 3, 3, 4, 4, and then multiply them together. Okay, but since we're adding all these, it doesn't matter. Okay, so now, any other questions about this expression? Okay, so let's apply our trace theorems. All right, starting with the simplest one, we automatically see that these two terms are going to vanish. Okay, that's why I need not worry too much about the sign. And our last two terms, we're going to make use of the expression on the equation sheet I gave you to reduce them now to factors of the metric, or actually the inverse metric. Okay? So just jumping to what that expression will look like. Actually, let me just, for reference, write down what this is. And I'm going to be really careful because, and you guys should note this. Let me see, where is it on here? There it is. All right, when you use an expression like this, you have to be faithful to the order of the indices when you're transcribing the right-hand side. You can't just arbitrarily just throw indices around. So if you'll notice in the expression on the equation sheet, the last index in their example is sigma. We're going to use beta. That's fine. Just replace sigma everywhere on the right with a beta. Okay? But you have to follow the order in the expression on the right. So just writing that down for reference, I'm going to have mu alpha lambda beta minus beta mu lambda beta alpha beta plus beta mu beta beta alpha lambda. And then this guy is just going to come out to 4 beta mu mu. Okay. Now coming here, mu alpha lambda beta, that was fortunate, and then mu lambda, all right? So when I do this, what you're going to notice, because I'm going to write down the evaluated expression, so I want you to know where it comes from. When we take this term, this is going to combine the mu and the alpha, so it's going to combine, or actually it's going to turn the index on PA into a mu, and this is going to turn the index on PB into a lambda, okay? However, this term, well, let me jump down to this term because it actually does something interesting. This term is going to take the mu and the beta, sorry, this term, this is the one I want, this is the one that's interesting. Too many indices on the board, I'm dying here. The alpha and the beta here is actually going to take these two p's and form their dot product. Okay, so I'm just going to write the expression, and then maybe it'll be easier to go back and just say, oh, I see where that came from, and I see where that came from. So here we go. So I've got 4p mu a p lambda b minus eta mu lambda pa dot pb plus p lambda a p mu b plus 4m a m b c squared eta mu lambda. Okay? So is everybody on board with where those terms came from? Again, that's just sticking in this formula for the trace over 4 gamma matrices, sticking in the associated formula for the trace over 2 gamma matrices, and then, I mean, this term doesn't really do anything interesting, but this does funny things with different p's. Okay? Now, as if that weren't bad enough, we then have to apply the same thing here. Okay? Keeping our indices distinct. So there's a lot of index tracking as we write down these expressions, but it's going to become very important because at the end of the day, that's going to determine what combinations of momenta are dotted into each other, right? So without any further ado, I'm just going to go straight to this guy. So the spin averaged and spin sum version of the square of M tree takes the following form. And just call out if I write a G. And now I'm actually going to identify what, so 1, 2, 3, and 4 are actually labels of particular particles. And then those particles have particular masses. So I'm going to go ahead and write these in terms of the masses of the particles they're associated with. So we are all right with that? I'm basically just copying down this expression applied to this trace. That gives me 4 times this, and applied to this trace, that gives me another factor of 4 hence the 16. Okay? But now, I can contract the indices. Because you'll notice, if we were careful, every term here should have a mu and a lambda. And every term here should have a mu and an alpha. But these 2 factors of the metric are telling me to combine mu and nu and lambda and alpha everywhere. Okay. So when I do that, my final expression is going to become just tidying up some factors. Everyone knows what I mean when I write a dot product here, right? If I write P1 dot P2, that means in this expression somewhere there was either something like that or something like this. And that is what this dot product means, okay? It's important because everything is now going to be in terms of dot products. Okay, now I don't expect you to actually follow that. I mean, you literally, you just multiply these things out, being very careful, I mean, you're multiplying these two things together, and then you're applying all of those factors of the metric, okay? But what do we notice? That's the answer, yeah. This is entirely in terms of form momentum. There are no spin elements left. So this completes at least the spin part of the construction of these amplitudes. We have completely removed all of the spin stuff. First by constructing spinner sandwiches, and then evaluating those spinner sandwiches in terms of traces, which are useful when we sum and average over the spin states, and then evaluating the traces themselves using the trace theorems. Okay. Yes?
Should the P1 dot P3 term be squared? That's what we first saw. Or should the
Yeah, I'm sure I made a mistake in writing this bad way now. Interestingly enough, P1 dot P3. Sorry, I'm going in a second. No, rather actually this should not be squared. Okay, well, I'm glad we've got 15 minutes left. I've got a lot to say. Okay, so, any questions? I know it's not the most exciting lecture. I'm not gonna lie, like, this is a calculation. This is like, Martin was the one who kept going, when are we gonna calculate something? When are we gonna get Martin's the one that's not here? So, all right, anyway. Martin, I hope you see that on the video. We all hate you. Now, we have to do this because at the end of the day, I mean, look, I'm a theorist and I like to just kind of dabble in the highbrow stuff, and I never really care too much about getting to numbers, but at the end of the day, you gotta compare the stuff to experiments, so you gotta get a number. All right, and the good news is we're halfway there. Okay, so I say we're halfway there because all we've got is this, but to use that, we've actually got to now go to the golden rule. We've got to actually analyze the process, okay? So let's recall that the golden rule for two-body scattering, which is what this is, two bodies come in, two bodies go out. The golden rule for two-body scattering simplifies the differential scattering cross-section can be written as, and this is a formula that we've seen before, this is the general form of it, we'll specialize this a bit more in this case. Okay, does that look vaguely familiar? Okay. Remember, for two-body scattering, there's so much kinematic constraint on the process that you can actually do the integral that's usually in the golden rule. And that's why there's no integral in this expression. Okay, so we're actually going to work, at least for this process, in a pretty reliable limit. So, first of all, this formula is good for the center of momentum frame. So that's assuming that you have zero net spatial momentum. We're going to assume two things. Well, we're going to assume that the mass of the muon times c squared is much, much larger than the energy of the electron. Okay? The energy of the electron would be the energy associated with momentum 2. And of course we know that the mass of the muon itself is much larger than the mass of the electron. Okay? Yeah.
The golden rule asks for n squared. What difference in our calculation do we get when we put in the average What does that have? An average cross, I thought a cross section, a differential cross section was just a probability.
You can ask for the differential cross-section for a specific outcoming polarization state.
So random.
You could set up your experiment with specified incoming spin states, and then the differential cross-section would be different than if you're sending unpolarized beams in. So this is effectively saying, what's the differential cross-section associated with sending in unpolarized states and then not looking for a specific polarization coming out, just recording all polarizations coming into a specific unit of solid angle. Okay. So now this is a very realistic assumption. This is a pretty safe bet, but fortunately now we have a situation which is kind of got some intuitive sense to it. We can think of the muon as this big ass thing, and you got this little electron, and this little electron is essentially going to come in and scatter off the muon, and the muon is just going to sit there. It's not really going to respond. Okay, this is much like a satellite scattering off of a planet. Okay, so we can make a lot of assumptions in this particular case. For example, we can assume that the momentum of the muon is effectively unchanged. We can actually make a really nice assumption, and that is that the center of momentum frame is actually the rest frame of the muon. Okay, if you remember your formula for center of mass of a system, if I have a really, really heavy thing and a really, really small thing, it's pretty much the center of mass of the really heavy thing. Okay? So with that in mind, I can actually start writing down some explicit expressions. So first of all, oops. If this is the initial momentum and this is the final momentum, okay, the direction can change, but if this is essentially 0 at the beginning and 0 at the end, then the magnitudes of the initial and final momentum are the same. Think of bouncing a ball off of the ground, right? The ball leaves the ground with basically equal and opposite momentum to just before it hit the ground, and that's essentially because the ground doesn't itself move. All right? So that means that this factor is pretty easy to evaluate. I'll leave it to Matt. Matt? Yeah, man, you're good. All right, sweet. This would be 1. Okay. Moreover, if we consider the sum of the energies, then if the momentum, if the muon is sitting at rest, then this is, so again, the center of momentum frame is where we should be working, but that's effectively the rest frame of the muon. So the energy of the muon, which is, oh, and I have this backwards. 1 is the muon, so this would be mass of the muon times c squared, that's the rest energy of the muon plus the energy of the incoming electron. But this is effectively the mass of the muon times c squared, because we're assuming that the rest energy of the muon is much, much larger than the total energy of the incoming electron. Okay. You could obviously crank up the energy of the incoming electron, but we're just considering these sort of medium energy situations to simplify this. Okay. So with that in mind, our expression for d sigma d omega simplifies a bit to the following form. Oh yeah, there's this this counting factor. Does everybody remember what role S plays in the golden rule? Yeah, it's for the degeneracy. If you have identical particles coming in or going out, then you have to divide by a degeneracy factor. All right. But of course we have distinct particles because Uncle Alex picked a nice process, right, where there's no degeneracy, so S is equal to 1. So at the end of the day, this expression is going to simplify to the following form. Okay. So we just multiply it by this. Yes?
So just for clarification, if we could have rotated that diagram, would that have made it degenerate? Is that what we're talking about when we say degeneracies? Like the ability to create different diagrams like that, or?
So the degeneracies that okay, so yeah, there's degeneracies in the diagrams themselves, and then there's degeneracies in the process, which is to say the golden rule is talking about the process. So it's not worried about how I actually fill in here. And so the degeneracy I'm talking about now is if I have an electron here, an electron here, and an electron here, okay, switching these two outcoming things is really not changing the process, because it's still an electron coming in this direction with whatever momentum and an electron coming out this direction with the momentum. It wasn't like this was a green electron and a purple electron. They're identical. So that's why you need this degeneracy factor. So even if I rotated this, I would then have a muon and an anti-muon. But that's a completely different process, actually. So but that's the degeneracy that we're talking about in the golden rule. Okay, so we need some expressions for the momentum vectors. And now you're going to see why we're working in this particular scenario, because these are going to simplify tremendously, because our momentum vectors, our four momentum vectors, are going to take the following form. So just lining things up, well, actually I'll just work in terms of the spatial vector. So the momentum of P1, which is the muon sitting there at rest, is effectively m mu c times and the zero vector. It has zero spatial momentum. P2, which is the form momentum of the incoming electron, well, that has some energy E over c and some incoming spatial momentum. P3, which again corresponds to the outgoing momentum of the muon, well, our assumption is that the muon is so heavy that it actually doesn't respond to the process, so it's the same four momentum vector as before. And then lastly, for the outgoing electron, it's going to have the same energy, and the only difference in momentum is the directionality. It's going to have the same magnitude of momentum, but it's going to be moving in a different direction. Okay. So now we can take these particular assignments and immediately see why some of this is going to simplify. When we do dot products, anytime you've got a zero in the spatial part of the dot product disappears. Okay. So I'll get to the dot products in a minute. To get started with, we have to evaluate P4 minus P2 in terms of something that's useful. So let me crank out what that's going to look like. So I'm going to start by writing this as the square of this difference. This is just 0. So this is two 4 vectors subtracted squared, and these are the two 4 vectors in question. So the timeline components are just going to be 0, E over c minus E over c, and then I'm going to have two spatial momenta, and then I'm going to basically take the magnitude squared of that 4 vector. Okay. So I pick up a minus sign there because remember the metric. When I take the dot product, I have to use a factor of the metric, and that reverses the sign for one of these factors. And now I can break this guy down. So minus P4 vector. I'll write P4 vector squared so you don't mistakenly think that's the 4 momentum squared. Okay, so I'm just multiplying that guy out. And now we can do a little bit of gymnastics, because remember the momentum P4 and the momentum P2 have the same magnitude, so there's really no reason to distinguish their magnitudes. Okay. And in remembering that the dot product is just the product of the magnitudes times the cosine of the angle between them, I can now think in terms of magnitudes, but the magnitude of P2 and P4 is the same everywhere. So I'm just going to call that P. So this actually reduces to minus 2P squared 1 minus cosine theta, and then with one of our favorite trig identities, relate that to the sine squared of half of the angle. Okay, so what I have in mind here is that angle theta between the incoming and the outgoing electron momentum vectors. Okay, so that's an expression for P4 minus P2 squared in this particular scenario. Yes, Rob?
Do you have to worry about like the angle between like the x components and the angle between the y components and the z components, or is it just kind of like the absolute angle between the two? So since we have a three-dimensional problem.
Oh, so a two-body problem is essentially a two-dimensional problem.
Okay.
It's like an orbit.
Oh.
Orbits can always be reduced to it. So it's a,
You always like look in the plane.
yeah, you can always look in the plane of the
Okay.
event. That's not guaranteed for more than two bodies. Well, actually, sorry. I'm sorry. For two bodies, you could have a non-planar event. Let me be careful. Yeah, you can have a non-planar event for two bodies. But since this guy is at rest, this has to take place in a plane. Normally, to get a non-planar thing, you have to have two things coming in and then going out in a, well, a line doesn't define a plane. So two things coming in at an angle so that there's a plane that's well defined.
Yeah.
And then two things that are created in a different plane.
Okay.
Right? But if one of them is sitting at rest and you have one coming in, that doesn't define a plane, it's just a line.
Okay.
But yeah, in a more complicated scenario, you would have to take those things into account. Okay, so banging out the last bit of this, now we can fill in what our dot products are. So starting with P2.P4, this is going to be, and literally this is just using the expressions for those vectors. Which I can reduce to me squared c squared plus 2p squared sine squared theta over 2. Can anybody guess how I might get from this line to this line? I heard somebody start saying it. Yeah, there's a few lines of algebra and you apply the mass shell condition. Okay, so that's written up in the notes. I'm just not going to go through that whole derivation now. I got to bang out the rest of these. P1.P3 is mu squared c squared, and then this last combination P1.P2, P3.P4 happens to be equal to P1.P4, P2.P3. Which itself is equal to the mass of the muon squared times the energy squared of the incoming photon. Okay, and I think we now have all the expressions we need to turn into this guy, giving a final result of the following. And it's actually not that bad. This is how you know you're getting close to something you can give experimentalists, because the expressions get simpler and simpler and simpler. I'm not being mean. It's like literally what you give an experimentalist this expression. Say, go measure this. Sorry, that was messed up. Okay. This is called the Mott formula. The Mott formula applies to even relativistic scattering, so I can send my electron in with relativistic energies. So, right? It's relativistic because we're doing relativity. It's built into it. But if we take the non-relativistic limit And in the non-relativistic limit, one way to phrase that is that the momentum squared of the incoming electron is much smaller than its rest mass energy. Then this simplifies. Alex, you can go ahead and ask your question while I write this down.
How can you use relativistic speeds with this if we assume that the energy was smaller than the rest mass of the muon?
Because a relativistic electron still has energy less than the rest mass energy of the muon. It's just the muon is so much more massive than the electron. Okay. But now, if I truly take the electron to be non-relativistic, then my expression reduces to this form, which some of you might or might not have encountered before. You guys seen this before? This is the Rutherford formula. So again, I don't find this stuff sexy. It's important because you have to connect all the formalism that we've developed to something that you can hand an experimentalist and say, go measure. Okay? So we can take a very large particle like a muon or a tauon, just some charged particle, and slam an electron into it, and then measure the rate at which we see the electron deflected at different angles, and it better satisfy either this formula if our electrons are moving relativistically, if we've given them enough energy, or this non-relativistic formula. This is actually something you can go and compare to experimental data. All right? Clearly, we could do better. This is, after all, a non-relativistic result, so we could go and take relativistic corrections into account. This is a tree-level result. We could go and take into account higher-order diagrams. This is making assumptions about the size of the muon compared to the size of the electron, or the energy of the electron. Furthermore, and this is probably the saddest part of it all, this is ignoring the other interactions. Those actually change the answer. Might not be obvious how at this point, but if all you're doing is saying I'm shooting an electron at a muon and I'm measuring what comes out, you've got to be ready for any possibility. And our calculation here has been based on a single diagram. How many actual diagrams contribute? An infinite number. So you can always do better. All right? But clearly, I hope I have impressed upon you that it just gets worse. So next time, or eventually when we talk about renormalization, we will come to a new type of diagram which we haven't seen. Well, we've seen it, but we haven't been able to evaluate it. I was going to talk about it today, but we're going to go ahead and go. And that is, what if you take this diagram and you actually include an internal matter loop? Okay, this is possible from the rules of QED, right? This is just a photon, particle, antiparticle, photon. We actually don't have a Feynman rule to evaluate this yet. I'll give it to you. If you were doing, well, this is relevant for your quiz. But anyway, you will learn a rule for doing this. Once we learn the rule for doing this, it's not a hard rule, but once we learn the rule for doing this, we're going to evaluate this diagram. And it is a diagram like this which is eventually going to lead us to the problematic infinities that we encounter. Because resolution is going to be the story of the normalization. Right? But we'll talk more about that.
Thanks for pushing the chair.
Oh, really? So I haven't seen you. So there's
No? Dude. Can you turn that off?
All right.